let's talk about DeMorgan's theorem. DeMorgan's theorem is a statement that says that a NAND gate is actually equivalent to an OR gate with two inverters on the front of the inputs. And it also states a second thing, that a NOR gate is equivalent to an AND gate with inverters on the front of the inputs as they're going in. We'll save that proof for another day, but let's go about showing that this one is true. First thing I'm going to do with this is break it into pieces that we can deal with a little more easily. So I'm going to redraw this as having an input A, sending it through an inverter, having an intermediate output of not A, and I'll do the same with input B, send it through an inverter, having an intermediate output of not B, and then I'm going to send them through my OR gate. Now this has just become an OR gate, and I'll have an output Y. So let's make truth table for this. We'll have an A, B, we'll have a not A, a not B, and we'll have an output of Y. And we'll see what the result will be. There are two inputs, so there's going to be a possibility of four outputs. A and B could both be 0, one could be 1, the other could be 1, or they could both be high. Now we're just going to look at row A for the moment. And we're going to invert everything we see because we're sending A through an inverter to get not A. So just looking at row A, I have low, low, high, high. So my not A is going to be high, high, low, low. Just looking at input B, I have low, high, low, high. And so I'm going to invert everything I see in row B. So I'm going to invert every low, high to a high, low, high, low. Now that I have that, I have these intermediary inputs, and I'm just sending them through an OR gate. And by definition, the OR gate, as long as you get one high input, you're going to get a high on the output. I've got at least one here. I've got one here. I've got one here. So this is the result. This is my result of this gate showing from my truth table is here. Now let's take a look at the equivalent part on the other side. We're going to also break this gate down into pieces. I could break it down into an AND gate and an inverter. And I'll make my intermediary output be X and my final one be Y. So let's make a truth table for this. We have two inputs, so we're going to have a possibility of four outputs. So I have A, B, I'll call it X and Y. So I could have them both low, I could have one high, I could have the other high, or I could have them both high. This is an AND gate, and by definition, they both have to be high in order to get a high out of it. So we're going to get an answer of, nope, they're not both high, not both high, not both high. Yep, they're both high. And we're simply going to send this result now through the inverter, and just, so anytime I get a low here, I get a high here, so we get high, 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 low. Now the thing I want you to notice here is we've just proven DeMorgan's theorem, where the resulting, every possible result is the same for these. So indeed, these two gates are equivalent.